This thing you see in front of you is the graphical representation of particles described in the Standard Model. Now if you don't know what that is, basically its main purpose is to try and describe everything. But not that thing. We still can't figure out gravity, so that is not included in this bundle. Gravity is God's way of giving you the bird when you try and figure out the universe. But other than that, we've figured out a lot. We've discovered that there are 17 fundamental particles, 12 of which are particles that make stuff, particles called fermions, and the others make stuff happen, which are particles called bosons. Since you probably only know where electrons come from, I'm going to take you on a quick tour of the subatomic universe. Let's start with this. If we take this and split it, we will have 2 halves of it. If we do it again, we will get 4 quarters. And if we keep going in this fashion, we will eventually get to its molecular structure. If we keep going some more, we will get atoms, then protons, neutrons, and electrons. And if we split a proton or neutron, we will get quarks, specifically up and down quarks. This isn't 100% true, but more on that in a later video. My point is, if you keep splitting something, you will eventually get to these particles. They make up everything. There are 2 main groups of fermions, quarks and leptons, both of which are separated into 6 types and grouped into 3 what are called generations of matter. The higher the generation, the more massive the particle, and unfortunately anything that's not a generation 1 particle will decay down until they are. This is because energy likes to distribute itself as much as possible. But getting back on topic, quarks. They make up all baryons and mesons. Those are just fancy names given to composite particles that make stuff. The quarks up and down, as previously mentioned, make up all protons and neutrons. The other 4 can be found in other baryons, one of which is the omega- particle. He contains 3 strange quarks, but unfortunately, particles like this don't live for very long, as the quarks inside them like to decay away since they're not generation 1. This is why you don't hear much about them. Moving on to leptons, they are separated from quarks in that they can't interact with a strong force. This is a direct result of their lack of color, and they are separated even further by charge. Electrons, muons, and taus are all charged, unlike their neutrino cousins. This allows them to form composite particles with other fermions. But the difference between the electron and his brothers is their mass, and how much they are willing to interact because of it. Neutrinos are completely neutral, as mentioned, which prohibits their ability to interact with things electrically. This basically allows them to fly through everything, only sometimes weakly interacting if they are feeling spicy. That's pretty much the only thing they are good for, weakly interacting and conserving lepton number. Now don't get me wrong, fermions are pretty great, but they are kinda useless if there are no forces for them to interact with. This is why neutrinos kinda just fly through everything. They can only interact with the weak force. The average range for this force is about 0.1% the size of a proton. For reference, the strong force has a range of about the size of a proton, and electromagnetism has an infinite range. So weak interactions, with their range being so small, are pretty rare. All other particles would be exactly like this, flying through each other, not even weakly interacting, if it weren't for the bosons of the Standard Model. They, in a sense, allow the forces of nature to happen. When 2 fermions act on each other with a force, they exchange virtual particles. This is just a fancy way of saying that fermions, in a sense, throw bosons at each other to either push them away or pull them in closer. A good way to think about how this works is by thinking of your friend on a frictionless surface. You just decided to throw a ball that weighs pretty much nothing at him, and you throw it at about the speed of light. When the ball lands, he starts sliding. The ball repels him away from you, meaning you just acted upon him with a force. In particle physics, this can either attract or repel your friend. There are 4 particles that fermions throw at each other that we have proven to exist. These are the gluon, the photon, the W boson, and the Z boson. To grossly simplify what each of them do, gluons allow quarks to stick together, photons let magnets and electricity, and as a result, chemistry, and pretty much everything you call existence to happen, and the W and Z bosons will break just about anything that can break. However, you might have seen this little guy over here and wondered why I didn't mention him. He is slightly different. He gives mass to particles that shouldn't have it. For example, every single particle on this model. It's hard to explain why they shouldn't have mass, but we know if a particle doesn't, then it should be traveling at the speed of light. This is obviously not true, so particles must have mass. The Higgs boson gives this mass, and does so by allowing them to interact with it. In a way, they get in the way of said particles, effectively slowing them down. It's a bit more complex than that, but this is a good enough explanation for this video. The Higgs boson deserves a video all to himself. To end this video, a quick recap. Fermions make stuff and are grouped into leptons and quarks. Leptons form composite particles with baryons and mesons, which are made of quarks. Bosons do stuff and allow fermions to be things. The Higgs boson gives everything mass, and this is all described by the Standard Model.